We have here two presenters. I don't see your name, sorry.
Melisa.
Okay, Melisa
and
Mara are going to present us this additional paper. Thank you.
Thank you. So good morning, everyone. I am Mara Soncin. I'm going to present this paper with Melisa Diaz, my co-author. Thanks. That is about how proficiency development affects future student performances. This is a joint paper also with Chiara Masci, that is here as well, and with Tommaso Agasisti, and all of us are from Politecnico di Milano. Okay, so here is the agenda. In terms of motivation, we know that Italy has a particularly high proportion of early leavers. These students before were somehow at-risk students. And we know that early warning systems prove to be effective to prevent student dropout and to detect at-risk students. Now the question is, how early? So of course, there is a trade-off between the accuracy of model that can predict whether a student is going to be at risk or not, and the earliness of this prediction. Fortunately, the increasing availability of longitudinal data allows us to track student proficiency and growth over time. In this respect, we can talk about growth models, and we can talk about growth description and prediction over time. Also, past research on early warning systems tended to focus on high school students, but we know that often students' disengagement happens in the transition between the elementary and the middle school. So probably going to look at the high school students may be too late. We also know that class and school factors play a relevant role in influencing student success, but actually also the variation of these factors over time may play an important role, and this factor is quite under-investigated instead. Finally, we know that the model does matter for this kind of identification models, and the question is, how precise are early indicators in the identification of at-risk students? This led us to our two research questions. The first one is descriptive in nature, and it is related to which are the factors that influence the transition from proficiency to non-proficiency and vice versa during the primary school, so between grade 2 and 5. The second research question is predictive in nature, and it is about to what extent longitudinal changes observed during the primary school can help us in identifying students at risk when they are at grade 8. In terms of data, for our first research question, our outcome is whether the student is downgrading or upgrading, so whether we can observe a decrease or an increase in the INVALSI score between grade 2 and 5. I will tell you in a while what do we define by downgrading and upgrading, while the second research question has as outcome whether the student is at risk or not. The student is defined as at risk when he or she is in the competence level 1 or 2 at grade 8. In terms of other covariates, we do have additional demographic information, previous academic achievement, and some environmental factors, in particular class factors, both in terms of level in a specific cohort and in terms of variation of these factors between the different grades. To define our outcome measure, so upgrading and downgrading, what do we mean? By, for example, downgrading, so first of all, we compare the distribution of the score between grade 2 and 5. We define downgrading those students that are in the top 40% of the distribution of grade 2, and they fall into the bottom 40% of the distribution of grade 5, and vice versa for upgrading. So those who are in the bottom and then go to the top. In terms of cohorts, we use for grade 8 for the second research question, the school year 2018-19 that is linked to the same student achievement of grade 5 2015-16, and then student achievement in grade 2. In terms of numerosity of these observations, we do have that the percentage of students downgrading and upgrading are nearly 8% and 7.4% respectively, while of course the vast majority of students are in this unvarying group. When we look not only to the distribution of students between the different groups, but also to the distribution of classes, so in how many classes are these students and in how many schools, we observe that actually these students are quite distributed across classes, as we are considering more than the 75% of the schools that do have at least one downgrading or upgrading student. These are the numerosity of cases for which we do have the longitudinal data, so grade 8, 5, and 2. Then we do have some missing information so that this final table contains the complete cases. In terms of methodology, for our first research question, we use a multinomial mixed effect linear model in which our output, Yij, is estimated for each student J within a school I, and is a categorical variable that can have three categories: upgrading, downgrading, or unvarying, that is our reference category. So basically we estimate a logit in which we compute the ratio between whether the student is upgrading and or downgrading over the reference category, that is unvarying, that is estimated as a linear relationship between a number of covariates at student and class level, as well as a random intercept at school level. For our second research question, we do estimate a logistic regression in which the output is whether the student is at risk or not, and we estimate the probability for the students to be at risk. So in terms of our first research question, first of all, we can describe a little bit our output. What we observe here are in green, the distribution of the unvarying students in grade 2 and in grade 5, while we observe that, for example, the upgrading students in blue are those who are in the bottom of the distribution of grade 2 and then go to the top part of the distribution of grade 5, where downgraded students are basically the opposite, so they are in the top and then go to the bottom. In terms of correlations between our variables, our covariates, here what we see are the different covariates both on the rows and on the columns. So on the diagonal, we see that the correlation is equal to 1. What we observe is that actually these covariates are not particularly correlated one another. There is a correlation with the teacher evaluation of the student of grade 2 and of grade 5. And then also between the delta class score between grade 2 and 5 and the peer score, so the INVALSI score at class level at grade 5. Now, in terms of results, first of all, for reading, what we observe here are the covariates that are significant in our estimation, while on the x-axis, we do see the marginal increment on the probability of upgrading or downgrading. What we observe is that there is a variable that is particularly significant, that is the delta class score. So basically the variation of the pupil score at class level between grade 2 and 5. What we observe is that an increase of 1 unit in this variable increases the probability of being an upgrading students by nearly 350%. At the same time, this same variable decreases the probability of downgrading by 75%. And this is actually visible also by looking descriptively at the distribution of the delta class score for the 3 different groups. In terms of other relevant significant characteristics, we observe that, for example, the higher the socioeconomic status of the students, the lower the probability to downgrade. But also for immigrant students, so being an immigrant student, either of first or second generation, decreases the probability to downgrade. We can interpret this also by looking at the distribution of these students. So these students are particularly overrepresented in the bottom distribution of grade 2. So these are students that actually struggle when they are at grade 2. So at least for them, the probability to struggle more at grade 5 reduces. In terms of mathematics, we do observe again this very relevant impact of the delta class score that is even larger in magnitude for mathematics. So basically here what we observe is a kind of peer effect, and it is estimated as a peer effect as the estimation for the student I is done considering all the other pupils in the class without the single student I. Of course, we think that here what the variable hide is very much a teacher quality effect. In terms of other differences, we do see that in mathematics, being a second generation immigrant also increases the probability of upgrading. Also, changing school between grade 2 and 5 actually increases the probability of downgrading. So there may be a kind of shock for these students over time. So now we stress the fact that class characteristics have an important role, but we also looked at the school effects. So here what we see is the distribution of the school effects on the probability of upgrading and downgrading, both for mathematics and reading. We see that between subjects, we see no relationship, while there is a positive relationship within reading and mathematics, where on the bottom, on the top, we do see those schools for which there is a positive effect both on the probability of downgrading and upgrading. So basically these are schools in which there is a lot of variety within school. On the bottom, we do have schools where actually most of the students remain unvarying over time. Finally, given that all our estimations were made on the 70% of the population as a training set, we could use the remaining 30% as a test set in order to predict also the fact that the student is unvarying, downgrading, or upgrading. We do observe that there is a little bit of misclassification between unvarying, downgrading, and upgrading, but actually the model does not do basically any kind of misclassification in classifying a downgrading student as upgrading or vice versa. So in this sense, the model is quite accurate. Now we'll leave the floor to Melisa for the second research question.
Thank you, Mara. So now that we, for example, have seen the factors that allowed a student to improve or decrease their performance in primary school, we wanted to see if the longitudinal changes during primary school allowed us to identify better students at risk at grade 8. So as Mara was saying before presenting the data, what we define as a student at risk. Students at risk are the student that doesn't manage to reach the level of sufficiency on the INVALSI test at grade 8. In the case of the reading test, we have that 29% of the students belongs or are classified as a student at risk. If we look descriptively, let's say the longitudinal transitions, we see that 41% of downgrading pupils during primary school are at-risk students at grade 8. Instead, the 45% of students that manage to improve their performance in primary school are at the top performances or above level 8. In mathematics, the situation changes slightly. So first, we have a larger proportion of students at risk in mathematics. We have almost descriptively the same effect of downgrading students. So if you decrease your performance in primary school in mathematics, you were more likely to become a student at risk, at least descriptively. Instead, only 32% of the students that improve their performances between grade 2 and grade 5, let's say, are at the top part of the distributions. The larger majority, let's say, of top performances are unvarying students, so students that remain constant in their performance over time in mathematics. So we use, let's say, the longitudinal changes as an input of a logistic regression model to estimate then the probability of becoming a student at risk. We also control for a different set of covariates like demographic information, previous achievement, and environmental students. We see that actually we also develop 2 models for each subject. So one of the models, we consider only all the covariates related with grade 5. So we want to see 3 years in advance if the student is going to be at risk or not at grade 8. The second model, we update the covariates with the information available for grade 8. For example, we update the socioeconomic status, we update the grades at the school, and the information that was available to be updated. We see pretty much in all the models that downgrading students increase the probability of become at risk, while upgrading students decrease the probability of being at risk only for Italian. That is also what we saw descriptively before. Instead, there is not a relationship mostly with improving your score in mathematics at primary school and then having an effect on the, let's say, grade number 8. Indeed, at certain point, for example, if we consider the covariates of grade 8, it could be detrimental for your performance. Technically, say, what we see in mathematics, that if you're an irregular student, you are more likely to become an at-risk student at certain point of time. Looking at the covariates, we are, let's say, have the expected results. So for example, a larger socioeconomic status decreases the probability of being at-risk students. Then we see also the relevance of the teachers' grades at the school, because having a large grade at grade 5 or at grade 8 decreases always the probability of being at-risk students. And let's say regarding, we also are able to see, for example, the geographical difference. So here, students from the south increase the probability of being at risk, while the student from the north decreases. And we see that changing the school, only the transition, changing the school between grade 5 to grade 8, which I think most of the students change the school during that period, affects so increase the probability of being a student at risk, which implies that comprehensive institutes, so the constant study over time of certain students in mathematics, reduce the probability of the study of the student to become at risk. We then look at the provisions of these models. We also kept 30% of our data to test the results. And we see here a clear trade-off between the accuracy and the earliness of the model. So we see that we have a sensitivity. So the capacity of recognizing at-risk students at grade 8 is higher when we use the covariates of grade 8. But it's actually not so high if we only use the information from grade 5. So we see that for reading, we're able to identify correctly 78% of the students who are at risk. And for mathematics, this percentage is of 74%. So technically, we're telling teachers, school, institutions, you are able to track with 3 years of anticipations the students we will have trouble later on. To jump into the conclusions, we have seen that for the first research questions, the class level factors and the transitions of the class level factors are significantly associated with the probability of improving or decreasing the students' performances. We have seen in particular that the improvements of the peer performances increases the probability of students upgrading by 4 or 5 times. So together with the peer effect, probably, as Mara was saying before, the teacher quality of the class is the hidden factor. Regarding the research question number 2, we have seen that the longitudinal changes are significant predictors to identify a student at risk at grade 8, especially for the case of the reading test. So tracking students' performances and changes at the primary school can significantly support the early identification of at-risk students. What are the policy implications? Of course, it will be ideal to identify the class characteristics then, if what is important is what happened inside the class, to then improve student performances. Then The other implication in terms of policy regarding the research question number 2 is to early track, the early tracking of at-risk students can start quite early on the school system. We have certain also limitations. For example, the definition of upgrading and downgrading is based only on a couple of observations. So we are, let's say, labeling student improving or decreasing only based on their test score. And we also have a discretional threshold. So we choose the 40% as a threshold, but we can also see or try to see what will happen if we change the threshold for different situations. The other limitations is that our reference group in the research question number 1 is very heterogeneous. So we have the really good students that remain the same and the really bad students that also remain the same. It will be, for example, interesting to see, only looking at the really bad students, the difference between those that improve and those that doesn't do, and the opposite for the ones that decrease it. So let's say this is a work in progress, but we're happy to see your comments.
Thank you very much, Melissa and Mara. Questions from home? I think that at this time you are quite late. I have a couple. No, there's a question over there. Please.
Your presentation was really very, very interesting. And what I think is that you have to create a sort of a tool to give to principal or to teacher just to prevent, you know, so because very often the research stays in the room of the research and school stay at school, you know, so this would be very important to create something so that you can tell to teacher, look, this student could be at risk, you know, otherwise it's not so easy for teacher. I mean, they just can tell to parents, but it's not so easy. I mean, if you have a scientific tool, maybe this could be very interesting.
Thank you. Yeah, we do agree that it's relevant to be able to, let's say, transmit the message of the research in general, especially if it can be helpful to target interventions for students that will be potentially at risk. We at the Politecnico will hopefully start a project that will allow us to, let's say, along with the minister and also along with INVALSI, to do something on that direction. Of course, it takes a lot of effort and a lot of time, but we are really hoping to do it.
Thank you. Other questions? Giovanni?
Thank you. I was thinking in line with the comment just made that we have some characteristics of the school system that can help to create some non-intrusive ways of give a signal to the teachers in order to, also not to clearly identify the students that could be stigmatizing. I was thinking about other tools in other parts in Europe that are pretty much stigmatizing. But in many, now many schools are organized around the Istituti Comprensivi. So there is the same principles, and the teachers of the secondary school and the primary school could gather as a policy tool. We could think about a more institutional standardized ways of gathering between teachers that take the vast majority of the kids in the primary school and that they follow them further, and increasing the communication between the two grades that is somehow just on paper could be very relevant if you also, without using the INVALSI data, so a hidden miss from INVALSI that say students 1, 2, 3, 4, 5, be careful. If you provide the teachers some insight on what they had to look for, also qualitatively, that might be a very cost-effective and easy way to do that.
Thank you, Giovanni. But just a comment. Okay, I had a question instead that is related to the way you presented class effect variable, the peer effect, teacher quality effect. If I'm correct, you showed us the graph where there is one deviation standard and the impact of one deviation standard.
So basically,
right?
We compute the odds ratio.
Yeah, and it is based on the one deviation standard of change in that measure.
Yes, basically.
I think that because I was wondering whether you are showing in that graph a huge effect due to the fact that you are using a huge jump in the class. I'm not sure whether there are so many classes in your sample where the jump of the peers is of one deviation standard. I expect that probably you are overestimating, not the effect, just overrepresenting that effect that is significant, clear, but it should be visually compressing all the other effects just because you're using a scale that is too large compared to the mean size of that change in the classes. So I want to know if you know something about the mean change that you have there, or if you can just in case in the next presentation try to see whether there is this distortion in this presentation. And the other thing that I was thinking is you frame your work in terms of risk of dropping out, and I would be much more happy to see a dependent variable where you combine both math and reading, because the students at risk of dropping out are the ones who are low performing in both subjects, and so probably it would be a smaller sample, but your model would be even more relevant in terms of prediction of future dropping out. These were my two comments.
Yeah, the second comment is, yeah, we can work on that for sure. On the first one, the only thing probably I can show super quickly, well, actually, there is also a difference in the mean. We do have these. Well, for example, here, that is the delta class score. And what is represented here is actually the mean for each of the three groups. So, but probably you're right, you're correct that we are somehow overemphasizing something that is there, but probably this
compressing a bit the other factors just because the bar is too long. That's it.
Okay, perfect.
Thank you very much. Thank you all for attending. I think we deserve a coffee now, but I think that our presenters deserve an additional applause. Thank you very much. Okay, enjoy your coffee, and thank you also to the people at home.